So I'll be talking about a very specific function today. This is a function that I have actually been interested in for a very long time, going back to my grad student days when my advisor, Paul Beame, told me about this particular problem. And well, it's been more than 20 years, but I'm glad to say I finally was able to solve it, but with a lot of help from many other people in the process. So I'll be talking about this function, which most of you are familiar with. It's an AND OR tree, so it has alternating levels of AND and OR gate. I've drawn a very general tree here with no restrictions on fan-in. It can be quite unbalanced. So you could have something like this. Something that looks like this, just alternating levels of AND and OR gates. And this is something that shows up very naturally in game tree evaluation. And so one of the key things that people in AI did was to realize that you can try to evaluate this game tree by using short circuit evaluation and save on having to actually have to query all the variables. So I'm interested broadly in the query and communication complexity of this of the AND OR tree evaluation. So by query complexity, I mean the number of variables that I need to query. It's basically a decision tree in order to be able to output the value of the function. And when I say communication complexity, I mean some arbitrary way of partitioning the leaf variables to some to Alice and some to Bob, and then what's the minimum number of bits required to actually compute the function under this partition. So I'm looking for the worst case partition. The worst case partition, right? And when talking about the communication problem, really at the level where you have, for those gates where the only inputs are leaf variables, you might as well assume the fan-in is 2, because if you have a larger fan-in like here, then because Alice can sort of combine the things belonging to her and Bob can combine the inputs belonging to him, and so therefore you can assume at the bottom level or at the level where the gates have only leaf variables as input, you can assume the fan-in is 2. So okay, so it's like a function. So why do we care about this function apart from the game tree thing that I mentioned? So let's look at some special cases, right? So I'm interested in what happens when the number of leaves is n. So let's look at some special cases. Okay, so what happens, say, if I'll try to draw some balanced trees here, so nearly balanced. So what happens if the depth is 2? Well, this is something that you probably are familiar with, because it turns out to be just so I'm looking at now the communication complexity version. This turns out to be nothing but the set disjointness problem. So already this is a very interesting function, and as Chin mentioned, this is one of the most studied functions with tons of applications. So already a special case is interesting enough, and we know that by Kalyan Sundaram and Schnitger and Rasborough, who introduced the famous corruption bound for this particular problem, that this actually has an omega n communication complexity. So then you can look at, so this is disjointness. Then at depth equals 3, you get something called the tribes. So there again you can say, okay, so at the bottom level there are two things, and so I'm looking at sort of a case where you have a fan-in of root n, another sort of root n approximately, and x1, y1, and so on. So it turns out that for this particular problem, you cannot use the corruption bound because both the non-deterministic and the co-non-deterministic communication complexity of this problem are square root n. Therefore, the corruption bound cannot push it to beyond square root n. Nevertheless, it turns out that it actually has a linear communication complexity bound, and this was basically something that was shown. This is something that work that I did a long time ago now, using information complexity. So, which was first introduced here, this notion of conditional information complexity, and this particular result itself is with Ravi Kumar and Shiva Kumar. So, okay, so already we see two famous this thing here. So there's the corruption bound, and then there is information complexity. So now the question is, what happens to larger depth? So to answer that question, it turns out the way you actually deal with these, at least in this case, when depth equals 3, is that you prove something called a direct sum theorem. I don't want to go into the details of what it is, and I believe Anup Rao previous session covered many of these things, but I realize many of you may not have been there. But that's not the focus of this talk. But just to say that once you do a direct sum type of thing, then it actually leads to another nice theory unto itself, which has to do with the geometry of communication protocols. So you have some nice connections where you can then talk about things like Poincaré inequalities and such. I'm just mentioning that because that's something that's quite interesting and has other applications. The problem in doing this type of direct sum type of argument is that you start to lose as you go to larger and larger depth. So the question is, what happens if the depth is large? And it turns out that the best lower bound that we were able to show, so for arbitrary depth d, so Leonardus and Sachs independently and with Swastik Koparty and Prasad Raghavendra, we were able to show something like n over, morally something like n over a to the d. Okay, and so you can, and this because you're losing as you keep doing this direct sum argument, so it doesn't seem to give the tight bound. So okay, so but why do we think that there should be what's the kind of bound that we're actually looking for? So this is something that let's look at the upper bound, right? So to understand what we actually want to show.
So in the model, when you have d, each level the fan-in is like the d minus 1 root of n, or is it like convenience in this case?
So d can be, so if it's a perfectly balanced thing, then yeah.
Is it like balanced in each level, like in this example?
So in general, it need not be, and this result applies, I think, to any any depth d with unbalanced. It can be unbalanced, right? So yeah. So for the balanced case, this result is not so hard to show, but it does expose the limitations of the direct sum argument already there. But it can be even shown for unbalanced trees. So right, so I'm now, for the rest of this talk, I'm going to be actually looking at this case of d equals log n. So this is the complete binary tree of depth log n, fan-in 2, and I will write the tree as actually, instead of as alternating and or, I will just by applying DeMorgan Loss, DeMorgan's law, you can say that okay, I'm going to write it as a tree of NAND gates. So these are all NAND gates. Okay, so you can ask, how do I actually compute this tree? I mean, let's even look at the query complexity world where you want to just query the leaves. So the idea is to use some kind of recursion, and this is something that would be probably taught in a basic course on randomized algorithms, and this is due to Sneer. So if I want to certify that this outputs a 0, right, that means that both of these things should actually be certified as 1, right? So that's the property of the NAND gate. On the other hand, if I say that this outputs a 1, then I know that at least one of them is a 0, right? Both could be 0, but at least one of them is 0. Now, in the deterministic thing, in case you don't know sort of which way to go, maybe the 0 is here, but you actually went here and you tried to evaluate it and it turned out to be 1, and then you're forced to do the other thing, right? But sometimes you could get lucky, and that's what short circuit evaluation is about, that you could actually, maybe if, on average, maybe you'll be half the time this side, and maybe you get lucky, and then you don't have to evaluate this side at all, right? You could turn this idea into basically a randomized algorithm, basically flip a coin and decide which side to evaluate, right? But you do have to pay attention, and this turns out to be important, to whether you're trying to certify whether it's a 0 or a 1. So if, for example, alpha sub d denotes, how many queries will I need to make if I have to, certify that it's actually a 0, then the recursion says something like, okay, I have to certify for 2 things of depth d minus 1 that is actually a 1, right? But on the other hand, you save if you're trying to certify it's a 1, because if you happen to get lucky and go this side, then you don't have to do the other side, right? So this leads to something like this. So this is the recursion. So this is large enough that you can see it back there. Okay. So you can work this recursion out, and then it turns out that the right answer turns out to be something like this strange thing. This turns out to be the solution to the recursion. I think for alpha d and beta d probably is also around this, about the same quantity. So I mean, this is strictly less than 2 to the d. So you are saving on something, okay? And so what Sneer showed is that you have an algorithm. If you express it in terms of the number of leaves, it's some irrational quantity in the exponent, okay? So this is the bound for this. The question is now, is this tight? Okay. So, okay. Okay, so we'll forget about the unbalanced case and we'll just focus on this particular function. So it turns out that is actually tight for decision trees. That's the query complexity model. And this was shown by Sachs and Wigderson. So they showed in 1986 that this is actually tight. So fine. Okay, so but the communication complexity of this problem has been open since. And that's what I want to talk about today, that we can actually get it pretty close to this. So what happened, right? I mean, we had this information complexity approach, but that didn't get us anywhere. So what has changed? What has changed is that there are some new set of techniques that are available to us thanks to some recent work which involves Mika, my co-author on this, with other people. So this is this idea of lifting. Right. So Yeah, I forgot to mention that a communication model can actually simulate the decision tree. So the reason is that when you get to a particular, you should take any decision tree algorithm, right? You're querying the leaves, right? It turns out that, I'm sort of cheating a little bit, that consider replacing each leaf variable, say by an AND gate. Okay, there's a leaf variable, but I then replaced it by some AND gate of, say, y7. Okay. Believe me that it's okay to do this, but then it turns out that querying a leaf variable is like exchanging one bit of information. Right? To figure out the value of that particular leaf variable, they'll just exchange x7, y7. So if I give you a decision tree algorithm that uses Q queries, then I can turn it into a protocol. Okay. The question is, can you do better, because it's a very restricted type of protocol. Yeah, thanks. I forgot to mention that. Okay. Okay, so let's get back to this thing of lifting. So the idea is that it's easy to prove this thing in the decision tree world. Sachs and Wigderson already did this for us. So why not use that and somehow lift that result into the communication complexity world? It turns out that it is not easy to do this at all, and we know how to do this only in the case of deterministic communication, and I'm interested in randomized communication. So what we know today, due to this result by Mika Gus, Shahar Lovat, Raghu Meka, Tom Watson, and David Zuckerman, is that you can take the function f and look at the following, lifted version. So you're looking at the communication complexity of f, which has n inputs, but instead of having variables here, I'll put a gadget here. And the gadget that I'll put is the inner product gadget. Okay? Which has a fan-in of b. Okay, its fan-in is about log n. So I'm actually looking at this function. Okay? So what is inner product? Inner product is a standard thing with, a parity gate with AND gates here. So strictly speaking, I should say this is 2 log n maybe, and so I have x1, y1, and so on. So I'm sort of blowing up the input from n to 2n log n, right? So I'm looking at the randomized communication complexity. So there's some particular, say, error parameter. So what they show is that this is omega of, you'd ideally like to say, the decision tree, that would be fine, but we don't have such a theorem. So we have it in terms of some weaker notion known as degree. Okay. So this is the result that I have. I have to tell you what this particular notion is. I'll get to it in a second. So, which means that I can, instead of living in the communication world, I can go into this degree world, which is not the standard degree that you might have seen before, but I'll get to that in a second, and prove a lower bound in that for that quantity. Okay. So that's what we do. We actually end up then looking at the degree of the and/or function and give a tight bound for that. Okay. Now you lose the reason I said you don't get quite this is because you lose some polylog factors. Okay. So this is morally right, but there's we have some losses that happen in applying this result. It's because part of the thing is that this has 2n log n leaves, whereas this has only sort of n, this is n inputs. So there's some loss, some log loss because of that. Okay, so that's one source of loss. Secondly, the function that I'm looking at is not and or, right? It's f composed with inner product, right? But that's not a big issue either, because it turns out that if I have inner product on k leaves, right, or 2k leaves, I can simulate that small thing itself by another AND OR tree with k squared leaves. Okay, so from log n, it becomes log squared n. Okay. Right, but it only blows up quadratically in the leaves. It doubles the depth.
The depth is not.
No, we're looking. The depth is, but the depth is only. If you look at the inner product thing on this, yeah. You take the parity, which is a binary tree of depth, log n, and then it doubles, and therefore you get log squared n. Okay. So you lose another log factor due to that. And there's a third loss of a log thing that comes in because this result actually holds even for small epsilon. Okay, you can make epsilon even as small as 1 over poly. Okay.
With that epsilon and the epsilon and the dv are two different epsilons.
This epsilon and this epsilon are the same. They are the same. Okay. In the way the result is presented in their paper, they are looking at constant epsilon, but it actually turns out to hold true even for subconstant. Okay? And the lower bound we can show is only for very, very small values of epsilon like 1 over n. Okay? In this talk, in fact, I'm going to show it for epsilon equals 0. Okay? So, but we can show in the paper we showed only for a very small value of epsilon, which means that if I go here, I'm only showing it for error 1 over n, right? Which actually, sorry, it should be correctness probability 1 over n, okay? Which I can amplify and take, another log n this thing, amplification. I may not be even saying this right.
Correctness probability 1 over n means you're being very gentle with the protocol, right?
No, I'm sorry. No, I'm saying that, no, it's 1 minus 1 over n. 1 minus 1 over n, right? So I'm showing it for, assuming that the error is very, very tiny, that I get a good lower bound. But I'm normally interested in constant error, so that's when the amplification can be used. Okay, so you use another log n factor. Yeah, my bad. Okay. But the extra stuff is another, so AND OR composed with AND OR is AND OR.
Right.
So ultimately F composed with, so what? F composed with IP, we are simulating with F composed with AND OR.
Yes.
But that's AND OR, it's just a larger number of leaves.
Right, but it's not instance specific then. I mean, you're bound,
So
you're not looking at the function, then it's making more generic over all of AND OR games. Is that what you're saying? Your result is not.
my result is very specific about the balanced AND OR.
Right, but apart from that, it's not. Okay.
Right, it's not a general enough thing that we have tried for general AND OR, right? But it does work for the balanced case. Okay. So for the rest of this talk, all I'm going to do is present sort of basically the kind of measure that comes up for which we can show, how do we actually show this thing, right? It turns out, it involves a sequence of steps, and all the sequence of steps are doing is to sort of identify issues with trying to prove such a bound, and I get to some particular definition. So all I'm going to be able to do is get to the definition of some complicated looking object for which we prove something. Okay, I won't be able to actually present the proof itself. So let's see where we are going with this. Okay, so first I have to tell you what this notion is. But the result is basically that if you can get a bound for this, then you get something for the communication complexity of AND OR. So what do I mean by this, and how do I prove such a lower bound? So as I said before, it would have been nice if this was just a query complexity instead of this complicated thing, but we don't know of such a result. But let's look at query complexity and in order to get to this particular definition. So what is query complexity? It's essentially decision tree, right? You query some variable, and then based on the the answer, you go left or right, and then you query some other variable, and so you have some particular path, and at the end you output a 1 or a 0. Okay, so if you look at a deterministic decision tree, it's basically, it looks like this, but from the deterministic decision tree you can extract these paths, right? So you have all these paths, right? And I'm only going to look at accepting paths. Okay, if you look at all the accepting paths, what does a path look like? It's a conjunction of variables, right? So it's a conjunction corresponding to this path P, right? So this is paths P such that I'll say that are accepting. Okay, so obviously I'm sort of, this is a one-way transformation, right? I mean, from given just some combination of paths, I mean conjunctions, it may not be that there's a tree corresponding to that. Okay, first of all, I'm sort of losing half the information because I'm only capturing accepting paths. So what happened to rejecting paths? So there's another expression for the rejecting paths as well. Okay, so this is about deterministic decision tree and giving this path. So by the way, this sum I can think of as actually, normally I would write it as a DNF, right? But it turns out I can even replace this by a sum because it's sort of in some sense a unique partition, right? An input will, if it is satisfied, it will be satisfied by at most one thing. So I can actually replace that by a sum. Okay. And the reason I want to write it in this way is because when I look at a randomized decision tree, it's nothing but a distribution over deterministic decision trees. Okay. So then what happens is that some of these paths can appear multiple times. Okay. And essentially you end up having some situation like this where you have conjunctions and you have weights corresponding to the conjunction, and this represents the AND of all the literals for that particular conjunction. Okay. So this is what a randomized decision tree gives me. There's one for the accepting paths and there's one for the rejecting paths. And if it represents a particular function f, say with error 0, and I forgot to mention for the rest of this thing we'll do it for error 0, then this actually equals f of x. Okay, because on the accepting things it of course evaluates to 1, and on the rejecting things we have all these things, none of the 0 inputs should ever be evaluated to a 1. Okay. Right. So this thing is called a conical junta. I don't know if this is the best choice of the term for historical reasons. I mean, if you have short conjunctions that evaluate things, we think of them as juntas, and we're taking a conical combination, positive in a non-negative linear combination, so they're called conical juntas. So, right. So I want to say, so there's one for f and there's one for also its negation, and you have to somehow look at both. Okay, but for the moment, let's just look at this particular thing and say, okay, amongst all the ways of representing f this way, I want something that minimizes something. So there's a measure associated with this thing. Okay, and the measure should be something corresponding to length of these paths, but averaged over all the trees that you see. So what that corresponds to essentially is that you're looking at the weights plus how long these conjunctions are. So you can say, what is the degree of this representation, right? So if this is if I call this representation h, then the degree of h is, and it's a worst case measure of the following quantity. Times the length of C. Okay, so this is the measure, sort of the cost measure, and then I can say the degree of f is the best h that represents f. Okay, and here I should say, I think that I will be measuring only on the ones here. Okay, because there's a corresponding thing for the zeros of the function. Okay. All right. So, okay, so this is our measure, degree. Okay, there's an epsilon here, but think of that as epsilon equal to 0. Okay. Degree is a real number. Yes. Okay. Okay. So if you now, okay, so we have this measure called degree. What can you say about it? Right? It would be nice if you could say the following. So I'm now moving into this thing called the composition theorem, and the reason for that is sort of the very nature of the and/or tree, the balanced tree, is that it's sort of, you know, it's intuitive to think in terms of, you know, something being composed of itself. So you may ask the following question: if I have, you know, say functions, right? So I have input z1, z2, zn. So what is the degree of f? Let me call this function p. So what's the degree of p as it relates to degree of f and degree of g? Okay. So turns out that, okay, take the conical junta for f, you know, it has conjunctions and you have literals, positive and negative. Replace the positive literals by, you know, conical juntas for g, and the negative literals by conical juntas for, you know, the complement of g. And so there's just a simple construction tells you something like this, okay, that it's times the max of this and this. Okay. All right. So it would be nice if this was tight, okay, but it turns out not to be the case. So the example that we have is that if you look at the degree of R of majority on 3 things. So it's the degree of, one of them is 2 and the other is 3/2. So the OR or the complement, they have different degrees. So OR is 2, no, OR is 3/2, the complement of OR is 2.
So this method will give nothing for set disjunct.
Possibly.
For the binary OR or for the?
Yeah, I'm talking about binary OR. Oh, yeah. So I think it's n over 2 for, yeah. So, okay. All right. So for this particular function, it turns out to be, okay. So it should be, if you look at OR, it should be, so okay, let me write down some things here. So degree of OR is 3/2, and degree of majority, this is on 3 bits, is 8/3, right? So you would expect it to be 4, okay, if you multiply these two. But it turns out, just brute force search, I mean, this is a simple enough function that you can figure out what the optimal choice of weight should be, that you can actually show that this is less than or equal to, I'm just saying that I have a construction that achieves 47/12. Okay. So, I mean, this is a surprise, right? I mean, it seems like a very natural thing to do, yet you have some sort of counterintuitive behavior here. And this, I think, points essentially to the hardness of, this particular problem, that it is not something that lends itself so easily to a very simple measure for which you can prove some kind of composition theorem. Okay. And there are several, and I must confess, even though I had this result with Mika, we neither of us we fully don't understand why it works, because we tried a bunch of things and something finally worked, and we have partial reasons for why simple things don't work, but we don't have a good explanation for why the final thing actually worked. It doesn't even look that intuitive, and my hope is that maybe it will get ironed out as we think more about it. Okay, so there's something about, there's this, even though I wrote this thing, it seems like they're probably losing too much by this process, because even in the recursion for AND or tree, and this is, I'm hand waving here, somehow you're charging differently for evaluating the 0 inputs versus the 1 inputs. And maybe this was too naive a way of sort of addressing that. That could be one partial reason. So, and that shows up in the measure that I'll talk about. Okay. Okay. So, how much time do I have?
15 more minutes.
Okay. All right. So I may not even get to most of the things that I thought I would, but that's okay. At least if you're convinced that this problem was hard, I'm happy. Okay. All right. So the way we do it is we actually write down an LP for this and look at the dual of it. Okay. So I can write down so there's a way to figure out what the optimal conical junta for a particular function is. And then you write down its dual. I won't write down the primal. I'll get to that later. Basically, the dual looks like this. So there are two certificates that you're looking for. Okay? And one of them you're probably used to seeing, but the other one is non-standard. So I'm fixing a function f, right? I'm trying to find the optimal, conical junta for this. So this is my objective, and I have the following constraint, which is constraints rather. One of which is that for all certificates, or rather all conjunctions C, I want to be less than or equal to okay, I'll try to parse this thing for you in a second. F is a distribution on the ones of F, on the S inputs of F. Okay? And this particular thing you can think of as Yau's lemma in action, that if you have some worst case measure, you look at the dual and that gives you some distribution on the inputs. Okay? So that part is fine. Phi, on the other hand, is unrestricted. It can be both positive and negative. Okay? And this is the part where the mystery of degree comes in, is that you are looking for some way of combining these things so that this inequality is satisfied. And so, okay, so the right-hand side of this you can think of as somehow the same measure that I was thinking about, the degree of something. Okay, this is like expressing the degree of the conjunction because I'm weighting it by its length, but I'm not doing it not as a worst case thing, but in some sense averaging over F. So you can think of it as some kind of averaged degree notion with respect to the distribution F. Okay, so this is not such an unnatural quantity, but yes, but you have this inequality and what to make of it. I mean, that's what the LP dual gives you. Okay. Okay. So we want to play with this particular thing, and as I said, because the composition theorem doesn't hold for degree, you can't hope to just use the certificates for F and the certificates for the complement of F and so on to prove your composition theorem. But nevertheless, the goal looks something like this, as is the standard when you're using, duality arguments. So what you want to do, sort of the high-level goal seems to be the following. Okay, that you're given certificates, phi 1 for F, phi 0, and two distributions F1 and F0. Okay, now I put the subscripts to indicate whether I'm talking about F or its complement. Okay, so F has this pair and F complement has, so this would be for F, and this would be for F bar. Okay, so you have 4 such objects that you're playing with. Okay, and G also comes with its own thing, right? You have gamma 1, gamma 0, and G1 and G0. So these are for F and F bar, and these are for G and G bar. And the nice thing about duality is that it's a constructive thing. If you can somehow take these certificates and produce a certificate for the function which is the composition of F and G, then that would be great. Okay? But because we know the composition theorem doesn't sort of hold for degree via that counterexample, this doesn't quite work. We are not able to do it. Okay? It turns out that, okay, this is the part where I start doing things that don't have a complete intuitive feel. Okay? So it turns out we can actually do something if we do the following. Okay? In addition to saying that, okay, these certificates exist, we will require that they actually have a particular special form, right? So the special form that we want is that they should be balanced. And by that, what I mean is that this should be 0. Okay? It seems like sort of an, just an ad hoc thing that you put up saying, let they have the balance property. The way we got into this was that we were looking at specific functions and we realized that the optimal ones had this property. Okay? So we decided, okay, what happens if we actually throw this into the mix and say the dual certificate should also in addition satisfy this? Because you're looking for some kind of induction thing that will go through, right? I mean, then you can make the composition theorem work, and then you would make it work for all levels for the AND OR tree. Okay, so I can throw this particular condition in and see what happens. Okay, now this I've thrown into the dual. Okay, you can also ask, okay, is this something that does it have anything to do with the primal? What does it say about the primal? Okay, so it turns out this is, if at all you got anything out of this particular talk, is it that this particular thing that we are doing seems to be not so standard and yet seems to be the key thing to prove this thing, which is that you are not actually looking for conical juntas that actually represent F. Okay? So what you're looking for, if you impose this condition and go back to the primal and see what it yields, is that you're actually looking for some conical junta representation, okay, that doesn't represent F, but some translation of F. Okay, so ideally you would have said, it should be 1 for things in the, for an F evaluates to 1 and 0 otherwise, right? That's what you were doing. But now you are saying, okay, I actually have the slack here, but it's the same slack for all values of X. Okay, and the slack is different for F and F complement. Okay, very strange. Right, so what I'm saying is that I'm looking for a weaker notion, right? That since I'm allowing the slack, I can get better representations, which the cost is the same. You still, tau does not enter the picture in terms of measuring the cost. It's just that you're giving yourself room to build other types of conical juntas. They don't represent F, but shifts of F.
So all values shift?
All values for the ones shift the same way, and for the zeros shift the same way in a different manner. Okay? All right. I have some other gap is entering the picture, and it's not clear why this was the right thing to do. Okay? No, sorry. So I don't think it is negative. I think that, sorry, if I understand it, this is not in the paper, by the way. This is sort of because you don't need to prove this to prove the theorem. So I think it is, you can do some rescaling and things, and it's something between 0 and 1, but positive, right? Yeah, so although I'm not 100% sure of that. Okay. If it maps to something that you know of, yeah, please come and talk to me, because it is something that I would like to really resolve as to why this is the one that works. We don't, of course, deal with the primal at all. We look at the dual and try to prove something. Now, it would have been nice if the story ended there. Unfortunately, it doesn't even end there. Okay. So in the end, I have just, it looks like less than 5 minutes. I will say that what we end up proving is for an even more restricted kind of dual certificate, okay, for which we don't have a primal analog. Okay, so that's another mystery associated with this, is that you end up with some kind of gadget, or rather some kind of certificate, collection of certificates that have a very restricted type of form, that they will look at something. Okay, I don't even think it's worth going through this. Okay, so I think I will not describe, because it will take me at least 10-15 minutes to describe this other thing that ends up actually doing the trick. Okay, but with this very, so we have a sort of 5 or 6 conditions on what this dual certificate should actually satisfy. But with those 5 or 6 conditions for F, and a similar number of conditions for G, you can prove a composition theorem. And magically, it gives you the tight bound even up to constant for the 0 degree of and/or function. I mean, you get the same recurrence as Sneer's algorithm. So I mean, so clearly it seems like something good is happening, because it's not like up to a constant of 1/1000 or something, and it's exactly the same thing. Okay. So I think it's worth exploring why this happened, and hopefully there is some simplification that makes it look more like, oh, we are actually doing some kind of new degree notion that we were not aware of before.
So what is the final composition theory? Just replace this direction?
Right. So you don't quite, because we don't have we have a collection of dual certificates that certify a particular value. And just like in the Sneer's algorithm, you had alpha and beta, you have 2 collections of values that you're tracking. As you so you take F and G, F comes with 2 values, G comes with 2 values, and the composition produces 2 values. So just like Sneer's algorithm keeps track of 2 things, these dual certificates certify 2 different things that you keep track of, which sort of obey the same recursion as Sneer's algorithm.
So do you have like an equality, like degree?
I don't. Because, I think it's too much to expect. The problem is that you need something where you're looking at F and its negation, G and its negation, right? You have to look at the negation of this composition too, right? If you're trying to build this up. And so you need something that looks at both a function and its complement. I don't think, at least for this purpose, you can write down a single measure. I think you need to keep track of 2 measures. At least that's what our result seems to suggest.
So you have all these other linear programs and tools which are lower bounds for communication, smooth rectangle, partition, all of these things. Do you see at all any relation between the tool that you're looking at the end and this kind of the other LPs that kind of know what they talk about?
Right. So all those LPs, if you look at it, they all lose something when you say, I'm going to convert it to communication, or whatever you want to do, you lose constants. First of all, they're probably dealing with the constant error, and they don't mind losing constants because they're going between one error to another. This thing is super sensitive to constants, because that recursion needs it to be tight. If I say, oh, it's not alpha plus beta over 2 plus, but alpha plus beta over 3, then you lose the thing. You don't get what you want. So in order to be super tight, you want to get the exact measure, and that's why you start encountering these mysterious things that you do not see in their results, because they are not dealing with a specific function. They are building a general theory for these things, like partition bound or something, right? So they are happy to lose certain constants. Yeah, so the moral of the story seems to be, when you're looking at a specific function, then maybe all this theory is not so good, and you need to be looking for other things. So.
What does it do for set disjoints?
Hmm?
If you were to apply this degree to the OR function?
No, so you get, for the OR function, you would get something like n over 2.
And so for set disjointness, you get omega n now?
Omega n you would get, but whether you would get the tight whatever in terms of epsilon, I'm not sure of. I mean, set disjointness is so well understood, we not only can say omega n, even in the BJKS paper, we were able to say n over 4. And now the Braverman papers and all that, they say even get tighter things for error epsilon.
No, but this will be a different proof, right? Oh, this only works for 0 error.
No, you can, then you can lose polylog. So you may get something like n over log n with via the lifting theorem. Yeah, this would give a different proof, not of omega n, but something like omega n over log n because of the gadget. For bounded error, yes. But that's not this thing due to us. Even their lifting theorem already gave that. Oh, wait, no. No, inner product, it kills you. I take that back. Yeah, it kills you, right. In fact, that's another open questions that they have. Can I do it for a constant size gadget? Right, so our gadget is in the GLM plus paper is this thing, right? Inner product gadget. Sorry, yeah, you're right. They don't get anything for set disjointness. Yeah, thank you.